You cannot hear it?
No.
Okay. Thanks God.
I mean,
Adding
I can hear some minor noise.
Cannot hear. Okay. I guess Zoom is filtering. So I reserve a ETF room, and I'm in the room right now.
Ah,
There's
I
a
see.
construction going on in the other side.
I see. I see.
We are live.
You're live?
Yes.
Okay, so welcome everyone to this semester processing memory PNS class here in ETH Zurich. I'm Geraldo. I'm a final year PhD student in the Safari Research Group. And together with Dr. Mohammed Sadar, we are going to conduct this semester's processing memory PNS class. So the goal of this first class is to give a brief introduction of what this class is going to be about. And we're also going to describe some of the projects that are going to be available for the students over here in ETH to conduct through the semester. In parallel with that, we are going to have weekly meetings or weekly lectures where we are going to discuss several research topics related to the topic of data-centric architectures. So this is going to be a brief summary of the lecture and what's processing memory. Feel free to ask questions or interrupt me at any moment. But yeah, I'm going to, even though I have a bunch of slides, I'm going to be quite brief. And the goal here is just for you to get like a sense of what we're going to cover during this lecture. So this is the schedule or the description that you might find in in ETH's website about this lecture or this PNS class on memory-centric computing or process memory. We are going to use those terms interchangeable here. And I want to highlight some of the keywords that you might find in the description of this class. So the main thing that you are trying to deal, or the main problem that you are trying to deal with in this class over here is that data movement exacerbates is a problem in current systems and is exacerbated by the increase in data demand for many applications like larger language models. You probably already heard that they require quite a lot of memory capacity to, and also memory bandwidth to be both trained and also run inference over, but we're going to also discuss this affecting other applications as well. So just an example of how data movement complicates the systems, prior work that we did in your group shows that for your mobile phone or some consumer workloads, which are not running the largest applications available, even though the system is quite small, data movement can dominate the energy consumption for that particular system. And this creates basically a data movement bottleneck for a series of applications. I mentioned large language models here, for example, but it's the same for other applications like bioinformatics, graph processing, databases, and so on and so forth. So the way that you're going to solve this data movement problem is by using or by giving a paradigm shift. So instead of centralizing the computation and using memory only as a passive component in the system, we are going to bring memory to the upfront of system design. And then we are going to design systems around the memory itself. So we are going to place computation where the memory resides with this paradigm that we call processing memory. So the goal of this project, of this class, is for you to get familiar with this first, this concept of identifying when applications suffer from data movement bottlenecks, how you can use tools to identify such a problem and pinpoint which is the main function, for example, that is leading to that data movement bottleneck. And then once you identify that bottleneck in the system, give you tools so that you can mitigate the data movement bottleneck using data-centric approaches. So this is the overview of this class. So our goal here, as I mentioned, first is to introduce you the concept of data movement bottlenecks. Usually when you look into code optimization, you mostly focus on time, for example. You don't focus so much on energy, but usually the time that the function takes is a combination of many of that function interacting with the system and going to the root cause of that part of a function that's taking a lot of time of your application is quite critical for performance analysis and optimizations. And once you recognize that the function might be suffering from data movement bottlenecks, you need to understand what are the workload characteristics that are leading to such data movement bottlenecks. So maybe your function does not make a good use of your cache hierarchies, or maybe your function is consuming a lot of memory bandwidth that your system cannot provide. So there are many cases that that function might be leading to, and all of those cases result in the observed data movement bottleneck. Then we are going to get familiar with traditional approaches to get to mitigate the data movement bottleneck, and also cutting-edge approaches which uses those new architectures called processing memory architectures to solve such data movement problems. We also want to give you some hands-on experience for the students here in ETH with several projects that relates to the topic of data movement overhead. So later on in this class, in the second half of this class, we are going to discuss this project that are going to be available during the semester, and then the student can later on select which project interests them the most, and then we are going to work close to one of our researchers in Safari to develop that project during the semester. So this is just an overview. So I keep talking about this concept of processing memory or data movement bottlenecks to alleviate processing memory to alleviate data movement bottlenecks in current systems. But even though just now we are seeing real products for processing memory architectures, this idea is quite old. So since the 70s, this is one of the first papers, if not the first, that talk about this concept of computing where the data resides. Since there, we already knew that data movement would create problems in the future because the way that you are designing systems. So, and people were already trying to think in a different paradigm, which could alleviate the data movement bottlenecks. However, just recently that we are actually seeing real processing memory architectures gain traction in the market. So now you have industry-based solutions that leverage those processing memory concept that was first proposed or discussed in the 70s, hitting the market to accelerate different applications. So in this class, we're going to discuss those architectures in more details. But one example is this PIM architecture from a company here in France, so close by to Switzerland. And but they are not the only ones. So main memory manufacturers like Samsung, for example, have been prototyping different types of processing memory architectures to accelerate, for example, large language model inference, and also other systems like recommendation systems. And this is true for other memory tech manufacturers as well. So as SK Hynix, and I didn't discuss here, but you also have not necessarily memory manufacturers, but other companies that are not necessarily in the memory business, like Alibaba, that are also thinking or prototyping such processing memory architectures. So in summary, the key takeaways for this PNS class is to allow you to get some more knowledge on computer architecture and processing memory, and technical skills into programming and architecting processing memory architectures and computer architecture simulators. When you're doing that, a key thing in computer architecture as a field is to you to think critically. So you always need to think about trade-offs and how you can better design a system, taking into account several different metrics at the same time, metrics that most of the time are contradicted to each other. So you're also going to have the opportunity to interact with, I say, nice group of researchers here in Safari. We are quite a large group. I'm going to mention that later on in the slides. But you're going to have the opportunity to see how big research group operates, and also with our current research directions. And finally, you're going to have the opportunity to deliver a technical presentation of your project that hopefully give you also some extra skills related to how to deliver a good technical presentation. So the goal here, as a field of processing memory or the class, is to teach you how to overcome data movement bottlenecks via different tools or different toolkits from the programming perspective, from the benchmark perspective, and use those new architectures, those processing memory architectures, to alleviate such data movement bottlenecks. So we have some prerequisites for this class. So if you are not super familiar with those concepts, we invite you to check the links that are the slides over here. Those slides are available in the class website that I'm going to mention later. But basically, you need to have some basic knowledge on digital design and computer architecture, or any equivalent class, like, for example, VLSI, and also some experience with programming. So you're going to work a lot with simulators the simulators might be written in C, C++, or Python. And in some of the projects as well, we are going to get involved with FPGAs, which uses some high-level programming, like C programming or C++ programming as well, plus the FPGA deployment of some particular tests. Also, we hope that you are interested in the future of computer architecture and computer paradigm, and you are eager to discover why things are not working and try to solve them by making the systems more efficient. So we are. So the Safari Research Group is led by Professor Onumutlu. He was a professor in Carnegie Mellon University in the US, and then he moved to ETH since 2015. And then we are mostly working on computer architectures, hardware security, and bioinformatics in our group. So this PNS is going to be mostly supervised by Dr. Muhammad Sadar and also by me, Geraldo. And we are going to have other PhD students and researchers in Safari helping conduct the hands-on project with their students. We are going to have the chance of meeting them when you discuss the projects later on in this class. So if you want to know more about Safari Research Group, you can go to our webpage. So this is just an old picture of the group in a highly saturated way. And we also have some newsletter that we publish with some frequency that describes or summarize our research activities for a particular period of time. And we also conduct as live seminars. So we try to make our research and also our teaching as open source as possible. So that's why we're live streaming this and recording those lectures so that we can reach a broader audience. But we also have some live seminars that are available online that discuss several of the research topics that we are going to discuss here in this class in more depth. And then you can check them on your YouTube channel. And we have some upcoming seminars that's going to happen later this month. So as I mentioned, our research is quite broad and it spans the topics of computer architecture, hardware, software co-design, and bioinformatics. And if maybe you are not necessarily interested on processing memory, but you might be interested in other things that our research group is being done, like, for example, bioinformatics or hardware security. And then this PNS might be a good door for you to figure out those topics later on. So regarding to the class itself, so we expect the students to attend all of our meetings. We are going to have weekly meetings, weekly lectures, if I'm not mistaken, on Wednesdays. I don't fully remember the time. Mohammed can confirm later. I think it's 10 a.m., but don't quote me on that. That's going to be available. Sorry, Mohammed, you want to say something?
Yeah, it is 10 a.m. You're right.
Yeah, so I'm correct. So it's Wednesday, 10 a.m. So you're going to have lectures of a particular topic related to processing memory. On top of that, you're going to have your own one-to-one meetings with your mentors, which are going to guide you through the project during the semester. So if you cannot join the class because you have a conflict, they are going to be available on YouTube, so you can check them offline. but please try to attend the one-to-one meetings with your mentors with the time that you're going to figure out by yourselves later on, or the time that works better for you and your mentor. So as I mentioned, each student, I guess this semester you're going to also have the group of students conducting some hands-on projects. And those hands-on projects cover broad aspects of computer architecture. As I mentioned, some of them are more simulator-based, some of them requires you to deploy something on a FPGA. And please, the most important thing is for you to learn. So please participate, contribute with thoughts and ideas, ask questions, and don't leave the project to the end of the semester, because that's not fruitful. So this is not a particularly demanding class. We don't have exam in the end. We don't have homeworks. So the teaching here is for your own gain. So you can take them in your own time. But the project is really important that you work a little bit on the project as the semester progresses. You don't leave to do all of the bulk of the work in the very last weeks of the project, because in our experience that never results in really good output for the class itself. So you don't learn, so you don't take the most out of the class if you do that. And ping the mentors as needed to get help on your project. Don't wait until the weekly meetings to get feedback on something that might not be working. So try to communicate as much as possible. And it have happened in the past that if your work, if you contribute to something, usually this something is part of a broader research topic that we aim to publish in top computer architecture venues. And if you contribute well enough, we probably going to be included in such a publication. And it's always good to have in your CV a publication in a top conference, for example. So as I mentioned, that we have the class website. Those slides are already available there. Over there, you're going to find all important links for this class. And you're also going to post the lectures over there. Also, please check your email with frequency, because we're going to make announcements over there. And we also have Moodle for Q&A, and also you're going to post in the Moodle a form for you to select your project preference for this semester. So again, this is the website for the class for this semester, the learning materials. And as I mentioned later on, you're going to discuss the one-to-one projects. So in the next meetings, you are going to talk about process memory architectures in a more depth. And also in the following weeks, you're going to start having your individual meetings with your mentors. And in the end of the semester, we didn't set the date yet, but in the end of the semester, you're going to have the chance to present our work to the Safari Research Group, the work that we developed during the semester. So we already have, I mentioned that we don't have homework, but we have one homework, homework 0. This is not a technical homework. It's just for us to get to know you more and know what your objectives to this class. So this homework is already available in the class website, and the deadline for that is next week before the next lecture. And so here is just for you to fill up some information about yourself. There is no technical questions at all during this homework, and you can fill it up and submit it over Moodle. Also, the Moodle link for the submission is already available. So you also have been giving this class in previous year. So I have copy and paste here the page website for previous semester. So you can check to see how the project or how the class usually goes. So I'm going to only continue talking for 9 more minutes before we move to the project descriptions for the semester. So, but before we get to the project description, I'm going to try to give the quickest introduction to process memory because I only have 9 minutes. But don't get worried about it. In the next lectures, you're going to go through those in way more details and in a better pace. I just want you to get enough knowledge so you can understand more or less the project descriptions that we're going to mention later on. So The main problem or the main thing that we are going to deal with in this class is the main memory system. So main memory today is a critical component in your system, independent of the system. If you use a server, if you use mobile system, if you're using a desktop or embedded systems. And the main property of a main memory in a system is that it needs to scale. It needs to stay scale in terms of technology, in terms of size or capacity, in terms of cost, and in terms of management. So that this entire system can scale as well. However, even though we have been designing this system, and this is a picture of a processor die, and everything green here is a part of the memory hierarchy. So even though you have been designing the system mostly to move data, so as you can see, most of that this picture is green. So most of the components in your system dedicated to either store or move data is still we suffer from data movement bottlenecks in current systems more than ever, actually, because applications become more hungry for data over time. Another aspect of that, other than just performance, is the energy aspect. Moving data in and out, the CPU consumes way more energy than doing computation. And this is just because the CPU is sitting in one part of the system and the memory is sitting in another part of the system. And this means that if your application is memory intensive, this data movement of moving data in and out the processor is going to dominate energy consumption and also performance for many applications. So this is just a nice plot that shows memory scaling in different aspects over the years. So as you can see here, we have been over since 1999, memory capacity have been scaling quite nice, and also memory bandwidth, but memory latency barely scale over the time. So this means that in terms of performance, if your application is memory intensive and requires is sensitive to memory latency, independently if you of the memory that you use, and we are going to end up suffer from some memory bottlenecks. And this is true for many applications, from database applications, graph processing applications, data processing, and data center workloads. So in terms of energy, as I mentioned before, the energy that it takes to do double precision computation is significantly smaller than the energy that it takes to move data from your main memory into your CPU die. So this number might vary depending on the system that you are analyzing, but the order of magnitude should be more or less the same. So from up to memory access takes 1, 2 to 3 more the energy magnitude or the energy consumption of doing a complex operation in the CPU core itself. So as I mentioned, this is not a new problem. So this is a plot from honors PhD thesis back in 2003, where you can see that most of the execution time for a collection of applications was dedicated to move data from the main memory to the processors. And then there is a more recently study from Google where they profile their server applications, and they saw that large portions of the execution time for those applications is dedicated to just moving data. And the main problem that creates this data movement and in terms of both performance and energy bottlenecks in current systems is that the way that you are designing the systems, and we are because we are performing computation really far away from where the data resides, and this is because of the way that we classically split the system. So we design systems in what is called von Neumann architecture, where the system is split into 3 main components: communication, computation, and memory or storage units. And then the computation always happens in a centralized way, so either in your CPU or in your processor, and data needs to be moved from the memory or the storage engine to the computation engine to the communication engine. So there is a imbalance on the way that the system is designed. Yet, as I mentioned, data movement becomes a main bottleneck in the system. So if you keep designing von Neumann architectures, we are going to always end up in a system that is mostly imbalanced, because computation is done only in a single place, only in your CPU, and everything else just stores or moves data. So either you're storing data or you're using interconnects to connect the cores to the memory device so you can move data. So this means that you create an energy inefficient system, a low performance system, and a quite complex system if your application, your key application is memory bottleneck. In the end, what we have been doing over the time is just to design the compute energy around this problem. So we are designing deeper and deeper cache hierarchies or more aggressive hardware prefetchers, and all of those are over there just to tolerate the energy and the latency that is incurred when you are moving the data from the main memory to the chip itself. And again, this creates energy inefficient and low performance systems. So this is just a description on how currently systems chip is designed. So you have several components that does computation. You have some interconnect that moves data in and out the system, and all of those interconnects together with this data movement creates this data movement over bottlenecks. So our idea here, or the idea of to fix this problem, is to be more data-centric. So instead of doing computation only in a given place in your system, we are going to do computation where the data resides. So if your data resides in your DRAM most of the time, there is no reason for you to move the data out of that DRAM. You should do the computation just there. If your data resides in your SSD most of the time, there's no reason for you to move the data out of the SSD to the DRAM, then to the caches, because the data is in the SSD most of the time. And then, as I mentioned, a large energy in current systems, a large portion of the energy consumption in current systems is spent on this data movement bottleneck. So just to summarize, we need paradigm shifts that allow us to compute while minimally moving data across the system. And for doing that, we need to compute where it makes sense, so close to where the data is. And to do that, we need to design a more data-centric architecture. So as I mentioned before, this idea and also this problem of data movement bottleneck is not new, but why we are thinking about this now? We are thinking about this now for two main reasons. The first reason is that there is a push from the application domain. Applications are becoming more and more data intensive over time. And you also have a push or opportunity coming from the technology. For manufacturing purpose, designing chips where you can have compute and memory in the same place is quite challenging, because those historically those manufacturing processes have been optimized for different purposes, which are contradicting to each other. However, due to packaging advancements over the time, like 3D stacking, now we can design computation in its own manufacturing process, and you can design memory in its own manufacturing process, and then we can use these advanced packaging technologies to glue them together. And so now we have a way of realizing those process memory architectures in a more feasible commercial way. So as I mentioned, the goal that we want is basically to tell my memory, do this query, do this function, and just return to me the output of this function. To do that, there are still several questions that needs to be answered, which we're going to try to cover in this class. So for example, which are the compute capabilities of the memory? So we don't want to design a full-blown processor inside the memory chip itself, because that will be quite costly and hard to cool down. So we need to think what are the minimum functions that we should include to this memory for accelerating important application or a broad set of applications. What is the software interface that we should use to communicate with the memory? What is the system what are the system changes that we need to do and to enable such process memory architectures. And all of those questions involve rethinking or going through the entire computing architecture stack, from rethinking algorithms down to how you design hardware in a data-centric way. So in this class, we are going to, I've been talking about process memory, but we are going to break down this concept of process memory into two main approaches. The first one is what we call processing using memory, where we are going to use the analog operating principles of the memory cells for computation, and processing near memory, where we are going to add computing logic near to the memory chips to do computation. I am already over time, but I'm going to really briefly mention, give an introduction of those two concepts so you can understand better what the project description that you're going to mention later on. So really, I'm going to go back into those more details in the next lectures. But basically, the idea of processing using memory is to minimally modify the DRAM chip to do computation. So here, we are not going to add logic to do something. We are just going to operate the memory chip in a different way so that we can achieve some function out of that memory, other than just storing data. One way of doing that, for example, is the row clone paper. So in this row clone paper, we show that we can do in DRAM row copy. Let me move here to this slide. So we can copy one DRAM row to another DRAM row by operating the DRAM chip in a different way other than the standard. So here we are going to, a DRAM chip works on this thing called activate. So you activate a row of DRAM cells. And what this row clone proposal basically does is instead of issuing activate and then reading the data out of the DRAM chip, we are going to issue back-to-back activation so that we can copy one source row to a destination row to the DRAM chip without the interference of the CPU. And this provides us quite significant energy and performance savings. Another thing that we can do by following such approach, so by issuing multiple activation to the DRAM chip, is in DRAM and the NOR operation. So if we activate 3 DRAM cells at the same time, basically we can do a majority of 3 of the values stored in those 3 DRAM cells prior to the computation. So basically we can do Boolean AND and Boolean OR using this triple row activation. So here we are not adding Boolean gates to do AND and OR. We are just issuing 3 in DRAM row activations to realize this in DRAM majority operation. So all of this was first proposed in simulation, but recently we have been doing some studies on commodity off-the-shelf DRAM chips. So those are DRAM chips that you can buy in the market, and we show that we can do a subset of those operations in the DRAM chips that are available already in the market. So we can, for example, simultaneously activate 48 rows in 2 neighbor subarrays in a DRAM chip, perform NOT operations, and also perform AND, NAND, OR, and NOR operations by following a methodology that I'm going to explain next. What we do basically is we have this FPGA infrastructure where we have our custom memory controller, which allow us to have fine-grained control over DRAM commands, and one of those projects are going to be related to this infrastructure. And by following a testing methodology where we issue a sequence of DRAM commands called activate, recharge, activate, we can generate those in DRAM row copies or in DRAM majority operations. So this is just a conclusion of this paper, and then later on in the project description, you are going to understand which are the projects what you can do next to improve these results, for example. Another way of doing process memory, as I mentioned, is processing near memory. And here we are going to move logic. So you are going to take the elements of a processor and we are going to put it near the memory chip itself, either in a 3D stack memory or near the memory controller, or inside the DRAM model itself. I'm not going to go into details on those, but basically, one way of doing that is using 3D stack chips, where we have layers of memory and layers of logic. And even though this idea have been first proposed in academia, now we have been doing experiments on those real chips, on the real DRAM chips that are capable of processing near memory computation. So as I mentioned, this is the PIM chip, which we have access to in Safari, and we can have projects related to those, and also Samsung chips as well, for example, to accelerate the recommendation system. And in the future lectures, we are going to talk into more details and over those. So to enable process memory, there are several challenges that needs to be addressed, and we are going to also address some of those challenges in the current in this current semester. And those problems goes from the application domain or to software domain, down to how to program those architectures, and more system topics like how to design compilers or runtime support for those process memory architectures. And as I mentioned, this involves going through the entire computer architecture stack, but we can go through those problems one step at a time. So if you are interested in process memory, we have a PIM book chapter that covers several of those topics that we are going to cover here in this lecture. And we have an upcoming version of this book chapter that's going to be available soon. So this is just an example of the topics in the book chapter. Also, we have been giving tutorials on process memory in Key Computer Architecture Conference. So we just delivered one in this June in the International Symposium of Computer Architecture in Argentina. And we have, upcoming one in Micro in Austin in the beginning of November. So this is that for the lecture part of today's lecture. I know that I went quite fast with the process memory introduction, but hopefully you understand more or less what you are coming from in this lecture. And in the next lecture, you're going to start dig deeper into all of those concepts that I brush in doing this lecture over here. So I don't know if there are any question available on YouTube or over Zoom. You can feel free to ask them. Otherwise, we are going to go to the project descriptions next. Okay, if